Okay, so one last topic that we'll be discussing in single phase AC circuits before we take up the three phase AC circuits is resonance. Uh, we'll be discussing two types of resonance. One is known as series resonance, another one is known as parallel resonance. The difference between the two is simply that one refers to a series RLC circuit and another one refers to a parallel RLC circuit. Fine. So resonance that occurs in a series RLC circuit is known as series resonance. The resonance that takes place in a parallel RLC circuit is known as parallel resonance. So first of all, what is resonance here that we'll be discussing? It is actually a frequency response characteristics of a system. So what does that mean? We have discussed time response characteristics. What does the time response characteristic mean? We have a variable that is actually a function of time. Say, for example, we have discussed so far voltage, current being a function of time and how it is sinusoidally varying with respect to time. So this is the time response behavior or the time response behavior of any function. Similarly, you will study different types of other functions that whose behavior you will be studying with respect to frequency. Fine. Instead of these functions being a function of time, instead of them being a function of time, we'll be taking them in the frequency domain and understanding them how they are varying, how they are behaving with respect to frequency. As frequency changes, how the amplitude or the phase of such systems is changing. Fine. Uh, so frequency response characteristics is actually something that we'll be studying in future क्योंकि इसमें आपको मैथ्स में पहले एक कोर्स पढ़ना है you'll be studying in engineering mathematics 3 course Laplace transform and so you're actually studying complex frequency. Now we have come across the terms. Say for example, for an inductor we have studied the reactance is j omega L. For a capacitance we have studied the reactance is 1 by j omega C. So you can see with omega there is a j term also associated, j omega L and j omega C. So this frequency now becomes a complex frequency, and how to analyze complex frequency mathematically and उनका फिर जो response behavior वगैरह है उस plot कैसे करेंगे, that you will be understanding once you take up that Laplace transform course in your third semester of mathematics. But for now, what we'll be trying to limit our understanding is to the fact that resonance is a frequency response behavior of a system. It is not a time response behavior of a system. That means, simply put, our system function is not now varying with respect to, we are not taking its varying nature with respect to time. We'll be considering its variable nature with respect to frequency of a system. So there are a number of definitions with which you can actually define resonance. One definition of resonance is it is actually represents that point in a system that behave. It actually represents that point in the frequency response behavior, or you can say in the frequency response plot, where impedance is purely resistive in nature. In other words, you can also say that the inductive reactance and the capacitive reactance, the magnitude of these two reactances will be equal at this point, and therefore they will cancel out the effect of each other. So the system will purely behave as a resistive circuit. Fine. So you have, uh, since we'll be first discussing the series resonance, we will take a series RLC circuit. So the capacitance, the inductor has a reactance of j omega L, the capacitor has a reactance of 1 by j omega C, and you are applying some voltage to this circuit, and because of which some current I is flowing in this circuit. So at some value of omega, what happens if omega is variable in this system? There will be some point, some value of omega. At that value of omega, what happens is that j omega L becomes equal to 1 by j omega C. Fine. Uh, since the total impedance of the circuit is Z equal to R plus j omega L plus 1 by j omega C, ये j ऊपर लेके R plus j omega L minus j divided by omega C. So you can see if omega at some value of omega L becomes equal to 1 by omega C. That some value of omega is represented by omega naught, and it is known as the resonant frequency. You have a series RLC circuit. By some means, you are able to vary the frequency of the system. There will be some value of frequency that I am taking here as omega naught, at which omega naught L will be equal to 1 by omega naught C. Since we know that the total impedance of the circuit is R plus j omega L plus 1 by j omega C, or in other words, we can write this as R plus j omega L minus j divided by omega C. At this particular point, what happens is that j omega L will be equal to minus j omega C. They will cancel out each other, and Z will be simply left equal to R in this circuit. So this particular point at which this happens, at which impedance of the circuit is purely resistive, the inductive reactance and the capacitive reactance cancel out each other. This point is known as resonance. This frequency is known as resonant frequency. Now, what is important here is our current I is equal to V divided by Z. So if we plot I with respect to frequency omega, fine. Let us take the magnitude of I. So it will be equal to Vm divided by magnitude of Z. So magnitude of I will be equal to Vm divided by magnitude of Z. ये जो complex number है आपका R plus j omega L minus j by omega C. Z is R plus j omega L minus 1 by omega C. So therefore magnitude of Z is R square plus omega L minus 1 by omega C square. Fine. So you can now take different values of omega, while Vm and R, Vm, R, L and C, they are fixed. You can take some constant value of the peak value of voltage, the peak value of resistance, inductance and capacitance, and you can vary omega. So you will see initially when you increase the value of omega up to omega naught, this current will increase, it will rise. So this will rise in this behavior. But beyond this point, as you keep on increasing the value of omega, 1 by omega C will now become more dominant as compared to omega L. and what happens is eventually the current starts decreasing. Fine. 1 by omega c now becomes less dominant as compared to omega L. Current starts decreasing. Now beyond this point, the current will start decreasing. So there was one particular point omega naught, where omega was equal to omega naught, that is at the resonant frequency. At this particular point, impedance is purely equal to Z. So you can directly say at this particular point I is equal to V divided by R simply. Fine. So you have the maximum value of current in a circuit, in a series RLC circuit, at which point? That is the resonant frequency point, at the point where omega is equal to omega naught. We are not discussing the behavior of current with respect to time. This is the behavior of current with respect to frequency. So if your frequency of the system is changing, what you will see is that initially the value of current will increase, but there will be a point where current will reach a maximum point, and that particular point is actually the resonance point, where impedance is equal to R. Beyond this particular point, the current will again start decreasing. So this is the behavior of current with respect to frequency. You already know how current actually behaves with respect to time. It is a sinusoidal variation. Current with respect to frequency will actually behave in this particular fashion, and this will be this is in this ये जो हमने particularly किया है, we have done it for a series RLC circuit, right? So for some other circuit it will take a different shape. It is not for it is not true for all circuits. Is only valid for a series RLC circuit. Current increases with increase in frequency, and then it at resonance it has the maximum value, and then it starts decreasing. So resonance can now also be defined for a series RLC circuit as that particular point where current has the maximum value. So you have now seen that as omega actually changes, the impedance of the system is changing, and impedance at a particular value, impedance becomes equal to R, where a circuit behaves completely as a purely as a resistive circuit, and current has the maximum value. Beyond this particular point, on either sides, the current value decreases. Fine. So this is actually the resonance in an RLC circuit. Particularly, we have actually taken a case of a series RLC circuit first. Current will increase, then have a maximum value, and then decrease. Now, what is the value of power at this particular point? At the resonant point, P average. यहाँ पे मैंने comma करके R लिख दिया. This means the resonant frequency point. The value of current will simply be equal to 1/2 of Vm into I. This is the average power in this system. We are not taking the RMS value, so it's 1/2 of Vm into I, whatever is the value of I here. Okay? So we already know the value of I here is actually Vm divided by R. So you can also write this as 1/2 of Vm square divided by R. So this is the average value at the resonant frequency point. There are on either side of this graph, there will be a point where the average power will be 1/4 Vm by I. ठीक है, 1/4 का मतलब है this is actually half of P average R. So that's why it's known as the half power point. So on either side there will be some value of current I, at which the average power in the RLC circuit will be half. This particular point is actually, since you already know that P average R is equal to 1/2 of Vm square by R. So how can you obtain from this 1/4 if you have Vm, if you choose a value of Vm divided by √2, तो square में वो actually रूट टू का स्क्वायर हो जाएगा, दैट विल मीन्स 1/2 1 into 1/2. So this particular point, at this particular point you can say I will be equal to root Vm by root 2 into R, or instead of writing Vm by root 2, that's Vm divided by 1.414, you can say simply 0.707 Vm by R. On either side of this resonant frequency, there will be a point, where the value of current will be such that average power will be half of the power that was obtained at the resonant frequency point. And so at this particular point, if average power is equal to P average, the average power at this particular point will be equal to P average divided by 2. Average power at this particular point will be equal to P average divided by 2. And you can obtain that if you substitute a value of I equal to 0.707 Vm divided by R. Fine. At the resonant frequency point, I is equal to Vm divided by R. At the half power frequency point, I will be equal to 0.707 Vm divided by R. I here is equal to Vm divided by R. P average at this case is 1/2 of V square divided by R. On either sides, here P average is equal to P average R divided by 2, and it can be, it will be, at this particular point the value of current will be 0.707 Vm divided by R. Okay. At the resonant frequency point, it is Vm by R. At this particular point, current will be equal to 0.707 Vm divided by R. This we have denoted by omega naught. This will denote by omega 1. This will denote by omega 2. So omega 1 and omega 2 are actually those frequency, those values of frequency at which the average power of this system is equal to uh, half of the power that is obtained at the resonance frequency point. So omega 1 comma omega 2 frequencies at which average power is half of maximum power value. So at the resonant frequency point, obviously since current is maximum, V being constant, average power at the resonant frequency point will be maximum, and therefore omega 1 and omega 2, you can also say they are those frequency points, they are those values of frequency at which average power will be half of the maximum power value. Therefore omega 1 and omega 2 are also known as half power frequency values, simply put. And the difference between these two, omega 2 minus omega 1, is represented by a term B. It is simply known as the bandwidth. So bandwidth of uh, so if you are talking about bandwidth in the series RLC circuit, it actually simply refers to the difference between the half power frequency values. We have not obtained the yes. Here P average was Vm square divided by 2R. Fine, we have found that. Now on either side there will be a point where P average, if I put instead of Vm, I have Vm by root 2. So at this particular value of voltage, this becomes equal to Vm square divided by 4R. So this is now half of this particular value. So this will only happen once actually omega is changing, current is changing. So this particular point at which current is equal to 0.707 Vm divided by R, Vm तो constant है, Vm actually change नहीं हो रहा है, but at that particular value of current, there will be a value of current at which power will be, yes, ये टू, कौन सा टू, which two are you ये ये तो ऑलरेडी 1/2 आ रहे हैं ना यहाँ पे, नहीं RMS RMS कुछ नहीं है ये, जो आपकी एवरेज पावर की फॉर्मूला इज 1/2 of Vm into I, फाइन, दिस इज valid at resonant frequency point. Now this is only valid at the time when omega is equal to omega naught. Now on either sides of this omega naught curve, the value of current is uh, decreasing. ठीक है, तो on either sides, if this we are assuming to be a symmetrical curve, on either sides of this frequency uh, of this particular graph, there will be a value of current जो कितना होगा, that will be equal to 0.707 Vm divided by R. ठीक है, हाँ, on either side of this frequency response curve, there will be a value of current at which what happens is that your average power will decrease. ठीक है, since आपका जो voltage वो already कम हो रहा है, so we have found that out from this particular graph. When will that happen? That will only happen when Vm is divided by root 2. So Vm divided by root 2 means it's like Vm divided by root 2, or in other words 0.707 Vm. ठीक है, तो when your current value is equal to 0.707 Vm divided by R, तो जब आप ये particular value लोगे and take this particular formula of average power Vm square divided by 2R, तो उस टाइम पे आप देख लोगे कि जो आपकी एवरेज पावर है वो हाफ ऑफ द मैक्सिमम पावर पॉइंट है, तो उस वजह से यू विल से दैट these particular values at these two particular values the power is half. So इनको इसीलिए half power frequency points बोलते हैं, and the difference between these 2 points is simply known as the bandwidth of this particular system. You can even take this formula, one half of I square R. ठीक है, क्योंकि average power at the resonant frequency point is also equal to one half of I square R. So this is only valid for omega equal to omega naught. For some other value of omega that I am taking that omega 1 and omega 2, there will be some value of omega where current is actually तो मैंने इसको एक्चुअली 0.707 लिया उस टाइम पे, स्क्वायर करके Vm divided by R. So when you substitute that particular value of voltage here, you will see that particular value of current here, you will see that average power will be equal to half of the power that was obtained at the resonant frequency point. ठीक, and the difference between these two is known as omega bandwidth. और जैसे मैं बता रहा था हमने रेजोनेंट फ्रीक्वेंसी की अगली एक्सप्रेशन नहीं निकाली. What we have established is that at resonant frequency omega L is equal to 1 by omega C, or in other words we can now say omega naught L is equal to 1 by omega naught C. तो ये omega naught square हो गया equal to 1 divided by LC. That means omega naught is equal to 1 by root LC. तो resonant frequency का अगर आपको value निकालना होगा, if you have been given a series RLC circuit and you want to actually know what will be the value of resonant frequency for this particular graph, you will substitute omega naught. You will simply calculate that from the values of inductance and capacitance. Omega naught will be equal to 1 by root LC. ठीक है. और अगर आपको इसको फ्रीक्वेंसी में लेना है, ओमेगा नॉट is equal to under root of 1 by LC. We know omega naught can be written as 2 pi f naught in terms of simple frequency f. तो f naught आपका 1 by 2 pi under root of LC हो गया. तो ये आपका रेडियंस पर सेकंड में था. This frequency, resonant frequency, this is also a resonant frequency, but this is in hertz. If you want to convert this into, if you want to find out this value in terms of hertz. So we have defined omega naught, we have defined bandwidth. There is another factor that we need to define for a resonant frequency, and that is known as quality factor. It is denoted by Q. Do not confuse it with the reactive power of a system. By the way, at this particular point, at the resonant frequency point, what happens is that जितना reactive power inductor store कर रहा है या जितना ये discharge कर रहा है, whatever amount of so whatever is the value of reactive power being consumed or generated by the capacitance, the same amount of value will be generated or consumed by the inductance at this particular point. ठीक है. So net reactive power actually at this particular point will be equal to net reactive power is actually exchanged is equal to 0, and this there is actually a generation as well as consumption of reactive power. Net reactive power will be equal to 0. That generation and exchange will actually take place between the inductor and capacitor. जितना इंडक्टर जनरेट कर रहा है उतना कैपेसिटर कंज्यूम कर रहा है, या फिर जितना कैपेसिटर जनरेट कर रहा है उतना reactive power inductor consume कर रहा है. So they will only exchange reactive power between themselves, and in other words we can say the net reactive power at the resonant frequency point will be equal to 0, although there is an exchange of reactive power taking place between these two particular components. Now we'll be defining the quality factor of quality factor. Quality factor is also known as sharpness of resonance. It's simply a factor that uh, quantifies or shows how effective our particular resonance is. Fine. And it is given by this formula 2 pi times energy stored divided by energy dissipated. So how much of energy is being stored in the circuit and this in a particular period. ठीक है. How much of energy is being stored in a circuit? It is actually a ratio of energy being stored over the complete actually in this particular circuit to how much of energy will be dissipated but in only one period of resonance. Now, energy stored in this circuit can be simply taken from the inductor or the capacitor. It is equal to 1 half of Li square, while as energy dissipated in one particular period of this resonance, it will be equal to 1 half of I square R, but multiplied with the frequency 1 by F naught. ठीक है, ये F naught यहाँ पे क्यों है? Because we are only seeing the energy dissipated in one particular period of this resonance. So this is your Q. So you can actually solve this. तो ये कितना आएगा? This will be equal to 2 pi F naught L divided by R. 2 pi F naught is, we already know it's equal to omega naught L divided by R. ठीक है? You can also take energy stored in this particular circuit is equal to 1 half of CV square. तो अगर आप वो फॉर्मूला यूज करेंगे तो Q आपका आएगा ओमेगा नॉट बाई आर सी. ठीक है, so you can take either of the two formulas. Quality factor is equal to omega naught L by R or omega naught by RC. ओमेगा नॉट भी एक्चुअली नीचे आएगा इस केस में. So Q is equal to omega naught L by R, or it is equal to 1 by omega naught RC. So quality factor is simply a ratio of two energy quantities. So it actually does not have any unit. It only quantifies our system, how effective our system is in. ये एक्चुअली दिखाएगा कि आपकी जो रेजोनेंस की कर्व होगी वो कितनी शार्प होगी. ठीक है, so that means is your resonance like this, or it is like this, or it is somewhere like this. ठीक है, तो कितना शार्प है आपका रेजोनेंस, that is actually denoted by the quality factor. So this means this particular value of resonant of quality factor means it is least selective. ठीक है, and this particular value of quality factor means it is having the greatest selectivity. It also actually points out to how much current is actually flowing into your system. What can be the peak value of current that will flow through your system? Fine. Q is equal to omega naught L by R, and or you can say Q is equal to 1 by omega naught RC. Q can be related with respect with it is also related to B, that is the bandwidth of the system. B is simply equal to omega naught divided by Q. Fine. Or you can say simply this is equal to R divided by L. So if you were to define the resonant, if you were to define the quality factor from here, quality factor is equal to omega naught divided by B. You can also define quality factor as the ratio of the resonant frequency to the bandwidth of this system. And from this particular value, from this ये जो आपका value actually आएगा, for that you actually need to know what is the value of omega 1 and omega 2 also. Omega 1 और omega 2 का क्या value है? Then you can only say what is the value of omega 2 minus omega 1. So how to find out omega 1 and omega 2? Omega 1 and omega 2 you can find out by substituting Z equal to R divided by root 2. So magnitude of Z you already know is equal to R plus R square plus 1 by omega L minus 1 by omega C square root equal to R under root of 2. So this particular value of omega 1 and uh, this particular value of omega that you will find from here will be actually nothing but omega 1. So if you solve this, you'll get omega 1 equal to minus R divided by 2L. ये एक्चुअली आपको क्वाड्रेटिक टर्म आएगी, यहाँ से आपको ओमेगा 1 ओमेगा 2 दोनों मिल जाएंगे बाय फ्रॉम द रूट्स ऑफ दैट. So omega 1 will be equal to minus R by 2L plus under root of R by 2L square plus 1 by LC. ये फॉर्मूला आपको याद रखने की ज़रूरत नहीं है. ओमेगा 2 is equal to plus R by 2L plus under root of R by 2L square plus 1 by LC. If you want to find out the values of omega 2 and omega 1, you need to substitute Z equal to R divided by root 2. Magnitude of Z is equal to R divided by root 2. This is a quadratic term in terms of omega. So from here you will get two roots. One will be omega 1, another one will be omega 2. So you can calculate these two values of omega 1 and omega 2. Now bandwidth is simply omega 2 minus omega 1. So from here you can simply see that omega 2 minus omega 1 is equal to R divided by L, क्योंकि ये और ये कैंसिल आउट हो जाएगा. R by 2L plus R by 2L, that is equal to R by L. Since omega bandwidth is equal to R by L and we know that Q is equal to omega naught L by R, so Q omega naught by Q equal being R by L, you can simply say that omega naught by Q is equal to bandwidth of the system. So ये कुछ formulas हैं जो आपको याद रखनी है. Actually you have to remember the formula for bandwidth. एक तो सिंपल फॉर्मूला ओमेगा 2 माइनस ओमेगा 1, दूसरी ये वाली फॉर्मूला है आपकी bandwidth is equal to omega naught divided by Q, where Q is itself equal to omega naught L by R or 1 by omega naught RC. Omega naught is equal to 1 by under root LC. F naught is equal to 1 by 2 pi under root LC. So these formulas you have to remember. These were all discussed for a series RLC circuit. Now we have a parallel RLC circuit. And instead of taking a voltage source now here, we'll take a current source. Since we are taking a current source here, that means actually our current is fixed for the system. The magnitude of current is actually fixed for the system. In the previous case for a series RLC circuit, we took voltage source. The voltage in case of a series RLC circuit, the magnitude of voltage remains fixed. In a series RLC circuit, for a parallel RLC circuit, the magnitude of current remains fixed. And instead of taking the impedance of the system, we'll simply take the admittance of the system. We know admittance is 1 by R plus J omega C minus 1 by omega L. ठीक है? Admittance will be simply equal to the summation of conductance and susceptance of the system. Conductance is simply 1 by R. इसकी जो susceptance है that is 1 by J omega L. इसकी जो susceptance है that is 1 by J omega C, that means J omega C. So simply adding these three terms, 1 by R plus J omega C and plus 1 by J omega L, or in other words J omega C minus 1 by omega L. तो ये इस particular case, इस particular circuit के लिए admittance value है. Now what we were defining there for in terms of impedance, now we'll be defining the same here for admittance. Now at a particular point when omega C is equal to 1 by omega L, what happens is conduct in not conductance, admittance is equal to 1 by R, or you can say simply conductance. ठीक है, denoted by actually G. So if your admittance of the system is simply equal to the conductance of the system, that means it becomes a purely conductive circuit without having any inductive susceptance or capacitive susceptance in the circuit, because they cancel out each other's effect. We'll say resonance has occurred in a parallel RLC circuit. So वहाँ पे इम्पीडेंस ले रहे थे हम, यहाँ पे हम एडमिटेंस ले रहे हैं. वहाँ पे हम बोल रहे थे इम्पीडेंस for a circuit is when a circuit behaves purely as a resistive circuit, that is Z is equal to R. Resonance occurs in a series RLC circuit. For a parallel circuit, we can say in our system admittance is it is having it's simply purely conductive in nature without having any susceptive value. ठीक है, we have defined admittance as G plus JB. ठीक है, we are saying here simply B is equal to 0, that is susceptance is equal to 0, only the conductance values remains. Even then the resonance occurs in the system. Whatever is the case, omega c equal to 1 by omega L, you will find that omega c equal to 1 by omega naught L, omega naught will still be equal to 1 by under root of LC. तो पैरेलल सर्किट के लिए जो हम डिफाइन कर रहे थे और सीरीज सर्किट के लिए हम जो डिफाइन कर रहे थे, the resonant frequency value still remains the same. Fine, it does not change. This is your in terms of radians per second, and in terms of, if you want to find out in terms of hertz, it's still 1 by 2 pi under root of LC. The resonant frequency in series RLC circuits as well as in parallel RLC circuit, it does not change, it is still the same. And quality factor का की जहाँ तक बात है, quality factor in this case will now quality factor in that case was equal to omega naught R by L, L by R. यहाँ पे उसका उल्टा होगा R divided by omega naught L. Or we said that quality factor for a series RLC circuit was equal to 1 by omega naught RC. So it will be simply here equal to R omega naught C. And therefore bandwidth in this case, instead of being equal to L divided by R, in bandwidth being, instead of being R divided by L, bandwidth in this case will be defined as L divided by R. ये फॉर्मूला तो वही रहेगी तब भी, bandwidth and quality factor के बीच में जो फॉर्मूला थी, that will still remain unchanged. Bandwidth will be equal to omega naught Q. But since Q has reversed in this case, bandwidth instead of being equal to L by R will be here, R by L will be here equal to L divided by R. You can also say it is actually equal to RC. In other words, अगर आप in terms of capacitive values निकालना चाहते हो, that's true for both series RLC circuit as well as parallel RLC circuit. Now instead of having a plot of current versus frequency here, we'll be having a plot of voltage with respect to frequency here. For a series RLC circuit, we discussed that I is equal to V divided by Z, और वहाँ से हमने करंट का वैल्यू निकाला. तो यहाँ पे हम V इक्वल टू I divided by Y लिखेंगे, I divided by admittance लिखेंगे. As the frequency of the system changes, the voltage increases and then it starts decreasing. So at a particular value, that is the resonant frequency value, the voltage value will be maximum. It will be equal to V equal to I divided by G, or in other words we can simply say V equal to IR. Fine, G तो आपका 1 by R है, तो this is V equal to IR at this particular point. Will be having the maximum value of voltage on either sides of resonant value, resonant frequency values. Voltage will decrease. and at a particular value of frequency omega 1 and omega 2, the average power will be half. At this particular value, P average will be 1 half of EMI. At this particular value, it will be half of that. And what value of voltage will be that? That will be simply 0.707 IR. ठीक है, वहाँ पे I इक्वल टू 0.707 V डिवाइड बाई R था, यहाँ पे आपका V इक्वल टू 0.707 IR है, omega 1 and omega 2. So these are half our frequency points in this particular case. So if you were to draw a comparison between series resonance and parallel resonance, basic definition of both the circuits is same. It actually refers to that particular frequency point where frequency is equal to 1 by under root of LC. ठीक है, and we get the maximum power at a resonant frequency point. So that is true for both cases. Now what changes here is that in this particular case, current is varying and having a maximum value at a resonance frequency point. In this particular case, voltage is varying and voltage will be maximum at the resonant frequency point. जहाँ तक ओमेगा नॉट की बात है, it is equal to 1 by under root of LC. Here also it is equal to 1 by under root of LC. Here also quality factor here is equal to omega naught L divided by R, or 1 by omega naught RC. Here the quality factor is equal to R divided by omega naught L or omega naught RC. You can say here the circuit is behaving as purely resistive circuit, as well as it's actually valid for both cases. You can say in either of the cases the circuit is behaving purely resistive or purely conductive in nature. ठीक है, तो Z यहाँ पे simply equal to R है, यहाँ पे आप लिख सकते हो admittance is simply equal to 1 by R or equal to G, that is the conductance of the system. Half power bandwidth वैसे ही bandwidth की formula same रहेगी, that does not change in the circuit.